Hello, welcome back to Cardinal Science for another Chemistry IGCSE video. Welcome to the first video on covalent bonding for the Edexcel IGCSE Chemistry 2017 specification. We'll be looking at points 1.44, 4.5 and 4.6. So first we'll be looking at what a covalent bond is, how that relates to electrostatic attractions in 1.45, and then we'll be looking at drawing dot and cross diagrams for the various molecules that you need to know for your specification. Okay, so of course to start with, we need to know what a covalent bond is. You'll probably have studied ionic bonding by now, and perhaps even metallic bonding. This is just a further type of bonding that we need to know about. Now, just like in ionic bonding, covalent bonds are formed because they provide stability to the atoms by allowing them to achieve a full outer shell. However, the difference between this and ionic bonding is that the electrons are actually shared as opposed to being transferred, and they occur between non-metals, as opposed to in ionic bonding, it was a metal bonding with a non-metal. So I'll illustrate this with a couple of examples. So I'll show you an ionic bond on this side, and I'll just show you a very simple covalent bond on this side. So starting with the ionic, say we'll do HCl, hydrogen chloride. So of course, hydrogen has one electron and a nucleus containing one proton, and chlorine, we'll just do the outer shell electrons here, has 7 electrons in the outer shell because it's in group 7. Okay, so the hydrogen atom needs to either gain an electron or lose an electron to have a full outer shell, and the chlorine could either lose 7 or gain 1. And of course it's a lot easier to gain 1 than lose 7. So what happens is this electron gets transferred over here, and that will form an H plus ion and a Cl minus ion that consequently attract each other, forming HCl. However, when we form covalent bonds, like I said, we don't have a transfer of electrons, they share electrons. So I'll show you the simplest one, and that is in a hydrogen molecule, H2. We refer to this as a diatomic molecule because, of course, it's made up of 2 atoms. So in this case, we'll draw 2 hydrogen atoms, and I'll draw them a little overlap, and I'll show you why. Okay. Now each hydrogen has 1 electron, and it would like, ideally, to have 2 electrons in that first shell, because of course that would make it full. So instead of transferring, because that wouldn't work in this case, what they do is they share their electrons between them. So I've drawn a dot for one of them from one hydrogen, and I've drawn a cross for the other hydrogen. Now, because these 2 electrons are in this bond, in the center here, each of the hydrogen atoms has access to both electrons. So the one on the left has access to the dot electron and the cross electron, and the one on the right also has access to the dot electron and the cross electron, and therefore they both have full outer shells of 2 electrons. Okay, now before we go into dot and cross diagrams further, we need to look at electrostatic attractions, because for 1.45 you need to know how electrostatic attractions relate to the formation of covalent bonds. If you remember, in ionic bonding, there are electrostatic attractions between the positively charged ion and the negatively charged ion, and that formed a strong bond. In this case, it's slightly different. If you recall, electrostatic attractions are attractions between oppositely charged things. That could be a proton, that could be an electron, or that could be an ion. So for example, you might have electrostatic attractions between a hydrogen ion and an electron because they're oppositely charged. It could be between a hydrogen ion and a chloride ion because they are indeed oppositely charged. Or of course you could have, rather unlikely but possible, a proton and say a chloride ion. Okay, so oppositely charged things have electrostatic attractions. Electrostatic attractions take a lot of energy to break. This is why covalent bonds are very strong, this is why ionic bonds are very strong, and this is why metallic bonding is also very strong. See my other video on metallic bonding for further explanation. Now, which of those combinations of different types of electrostatic attraction do we have in covalent bonding? Well, as I showed you just now, and I'll show you again, so imagine this is your hydrogen molecule. So you've got your nucleus containing 1 proton, and it's got a positive charge, you can see in the center, and there are 2 of them. Okay, and there's 1 electron here and 1 electron here, and they have both now got full outer shells. But where are the electrostatic attractions? Well, each of these electrons that I've done in blue are negatively charged, and each of the nuclei are positively charged. Therefore, the electrostatic attractions in covalent bonds are between the positively charged nuclei of the atoms and the shared pair of electrons. This is key because exam questions often ask about this, and if you use the phrases I've used here, you'll get the marks. Now, thankfully, with dot and cross diagrams, there's a limited number of molecules you have to be able to draw. So rather than just explaining the theory and expecting you to be able to do everything, I'll run through every single molecule that you need to know how to draw in this video. That way, if you are stuck with how it actually works, you could after all just memorize the structures of each one and get full marks. So let's start, shall we? We've done hydrogen. Okay, I'll do it again very quickly. Each hydrogen has one electron in the outer shell, and it requires one more, and therefore forming a single bond with 2 electrons in the bond there, and that's your hydrogen molecule. Dot across diagram, finished. Oxygen. Oxygen is in group 6. It forms O2. There are 6 electrons in the outer shell of each oxygen atom. And what happens there is that, of course, each one requires 2 extra electrons. And so what they do is each one donates 2 electrons to the bond, as you can see here. And now, if you count them up, so I'll do that slowly, so you'll see that each atom has access to 8 electrons. So the one on the left has got 1, 2, 3, 4, 5, 6, 7, and 8. And the one on the right has got access to 1, 2, 3, 4, 5, 6, 7, 8. We call this one a double bond, okay, because of course each atom has donated 2 into the shared electrons. There are 2 electron pairs, okay, so that one is a double bond. And our hydrogen formed a single bond. Okay, number 3, nitrogen. Nitrogen is in group 5 and has 5 electrons in the outer shell. It also forms a molecule that's diatomic, and therefore we can draw 2 overlapping circles. So 5 electrons in the outer shell, of course, means that there should be 5 in each of these shells, but where do we put them? Each nitrogen requires 3 extra electrons to have 8, which would give it a full outer shell. So what they'll do is each one will donate 3 electrons into the bond, and the remaining 2 electrons from each one will stay in the shell. Now again, we'll count them up just to make sure we've done it correctly. We want to make sure each atom has access to 8 electrons. So doing the left, we've got 1, 2, 3, 4, 5, 6, 7, 8. There are 6 in the bond. And looking at the right, we've got 1, 2, and then the 6 in the bond makes 8. Of course, unsurprisingly, this one is referred to as a triple bond. Then we move on to the halogens. Now the halogens are any of the molecules in group 7, okay? So that would be F2, Br2, and I2, and Cl2. I'll draw one of them, but of course it's the same for all of them because we're only doing outer shell electrons here. So if I was to do fluorine, which is in group 7, of course we're going to have 7 electrons in the outer shell. So each one needs to have 1 extra electron to have 8 and a full outer shell, which means we'll form a single bond. So it's just like you would have seen in hydrogen, except there are electrons in the shells. So we've got a single bond, and then we've got 6 other electrons outside. And if you count those up, you'll see that each fluorine atom now has access to 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. And of course, 1, 2, 3, 4, 5, 6, 7, 8. And now we know we're done. And like I said, this one I've just drawn could be fluoride, rather it could be fluorine, could be chlorine, could be bromine, could be iodine. This would look identical. Now with the last one, we're doing hydrogen halides. So when you get a hydrogen atom with 1 electron in the outer shell, bonding to any halogen, okay, so fluorine, chlorine, bromine, iodine. What I'm going to do for this one, I'm just going to put an X there to indicate any halogen. Okay, so the hydrogen needs 1 extra electron, and so does the halogen. The only difference being that the hydrogen doesn't have any other electrons. So the hydrogen donates its 1 electron into the bond, and the halogen donates 1 electron, but it also has 6 left in its outer shell. Now when we count this one up, we've got to be careful. So hydrogen, because it's on the first shell, only wants to have 2 in total. So the hydrogen has access to 1, 2, and the fluorine, the chlorine, the bromine, the iodine, whatever it is, has access now to 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so let's have a bit of practice now. There are 3 here that I haven't done yet, but you should be able to do based on that last page. So, draw dot and cross diagrams for the following molecules: Cl2, HF, hydrogen fluoride, and Hi, hydrogen iodide. Pause the video now, have a go, and then we'll go through them. Okay, let's go. So, what do we know about chlorine? Chlorine's in group 7, so therefore it has 7 electrons in the outer shell. We know it's Cl2, so we know we have 2 atoms. 7 electrons in the outer shell means, of course, it needs to gain 1 extra to have a full outer shell, which means we're thinking a single bond. So it's going to be 1 in the bond, and that's 3, 4, 5, 6, 7. Same for the other side. 1 in the bond, 2, 3, 4, 5, 6, 7. And that, of course, means that each one now has access to 8 electrons. Hydrogen fluoride. Hydrogen has got 1 electron in the outer shell and needs to gain 1, and fluorine has 7 and needs to gain 1 as well. Therefore they can form a single bond because they both need to gain 1. Hydrogen's electron goes in the bond, fluorine's electron also goes in the bond, and then of course there are 6 others. And if we count them up, we're going to have 2 electrons available for the hydrogen and 8 for the fluorine. Exactly the same for hydrogen iodide. I will draw it though, but you'll see that they're exactly the same aside from the label that I give it. So I'll put an I in here instead of an F, and again we have 1 electron from the hydrogen, and we have 1 electron from the iodine, and then of course the remaining 6 in the shells, meaning that we have 2 available for the hydrogen and 8 for the iodine. Okay, so here's where things get a bit interesting. We've got some slightly more complicated molecules. We'll do them one at a time. Water, ammonia, and carbon dioxide. So water is H2O. So we have 2 hydrogen atoms and 1 oxygen atom. And I'll draw them up here for you. So we get 3 atoms bonded together like this: a hydrogen, an oxygen, and a hydrogen. Hydrogen has 1 electron in the outer shell and will form a single bond so that it can have access to 2. And each of the hydrogens will do that, forming a single bond with the oxygen. The oxygen is in group 6, needs to gain 2 electrons, so it needs to form 2 single bonds to have a full outer shell. And so it will form a single bond with 1 of its electrons over there and 1 of its electrons over there. Now of course it has 4 electrons spare, and they will stay in its outer shell like this. Okay, so let's just check then. The hydrogen needs to have access to 2 electrons, and it does. 1, 2. So does the other hydrogen have access to 2? 1, 2. The oxygen needs to have access to 8, so there's 2 in each bond, so that makes 4, and there are 4 in the shell, so that also makes 8. So we're happy. Okay, let's move on to the next one, ammonia. Ammonia is NH3. So what we're going to have in ammonia is a central nitrogen atom bonded to 3 separate hydrogens, NH3. Now nitrogen is in group 5, and so it needs to gain 3 electrons to have a full outer shell, and each hydrogen needs to gain 1. Therefore we'll get 3 single bonds. So let's do this one at a time. So 1 single bond here. We'll just put the hydrogen electrons in first. That's our hydrogen electrons done. Now the nitrogen has 5 electrons, and it will put 1 into each bond, forming 3 single bonds, and it has 2 left over as a lone pair over here. Now if we count them up, as always, we have now 2 electrons available for this hydrogen, 2 for this hydrogen, and 2 for this hydrogen. And if we count up for the nitrogen, we have 1, 2, 3, 4, 5, 6, 7, 8, and everyone's happy. Okay, so the last one is carbon dioxide, CO2. So that's one carbon atom with two oxygen atoms. So we draw them nice and big to make it clear. So we have one central carbon atom with two oxygen atoms, one either side. Oxygen is in group 6, so it has 6 electrons in the outer shell. So it will need to gain 2 to have a full outer shell. Carbon is in group 4, has 4 in the outer shell, and therefore needs to gain 4. That means it can either have 4 single bonds or 2 double bonds. In this case, we're going to form 2 double bonds. So each oxygen donates 2 electrons into the bond, and the carbon puts all 4 of its electrons into the bonds. And of course, the oxygens have remaining electrons in their shells. So they have 1, 2, 3, 4, and 1, 2, 3, 4. Let's just count them up to be sure. So the oxygen should have access to 8. So it has 1, 2, 3, 4, 5, 6, 7, 8. This oxygen should also have access to 8. 1, 2, 3, 4, 5, 6, 7, 8. And the carbon should have access to 8. And since there are 4 electrons in each bond, it should be 8. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, organic molecules now. A little bit more complicated, but exactly the same principle. We'll start with a more simple one, methane. So methane is CH4. So what we have is a central carbon atom and 4 hydrogen atoms bonded to it covalently. Now each hydrogen has 1 electron in the outer shell and will form a single bond, and the carbon has 4 electrons in the outer shell and can therefore form 4 single bonds to get a full outer shell. Therefore we get 4 single bonds forming, and that is us complete. And of course we could count them up, but I'm sure by now you're tired of me counting to 8. There should be 2 available in each hydrogen and 8 for the carbon. Okay, the next one is ethane. Ethane is C2H6. So what we have in this one is 2 carbons bonded to each other, each one bonded separately to 3 hydrogens. So since we know that carbons can form 4 single bonds, what we're going to have is each carbon bonding 3 times to hydrogens and 1 time to the other carbon. So I'll show you each one. So you've got the single bond forming here, single bond forming here, single bond forming here, and the single bond forming here. Now if we count up the electrons for just these ones, we've got 2 for each hydrogen and we've got 8 for the carbon, which is correct. Again, the carbon on the right donates 1 electron to each hydrogen and receives 1, and therefore we are now complete. The carbons both have access to 8 electrons and each hydrogen has access to 2, meaning they all have full outer shells. Okay, our penultimate one, ethene. That one is C2H4. Slightly different because we have a double bond now. So what we have in this case is a double bond between the 2 carbons, and therefore each one can only bond 2 hydrogens to it. So C2H4. So here's how we draw it. So each hydrogen still forms a single bond with each carbon. Form a double bond between the 2 carbons, so with 4 electrons in the bond, and of course single bonds over here. And of course we can check this, so we'll count up our electrons. So each hydrogen has 2, and each carbon has 1, 2, 3, 4, 5, 6, 7, 8. And likewise on this side, 1, 2, 3, 4, 5, 6, 7, 8. Okay, now this last part where it says, and those containing halogens. So we're thinking the same situation, except one of the hydrogens in these molecules is going to be switched out for a halogen. So that's fluorine, chlorine, iodine, bromine. Now these behave exactly the same way as hydrogen does, except of course that they have 7 in their outer shell, and therefore there'll be 6 electrons left in that shell once you form the bond. So for example, if we were to do chloromethane, okay, so that's going to be CH3Cl. It will look just like a methane. I'm starting to use red now. But just like a methane, except 3 of them will be hydrogens, 1 will be chlorine, and when we draw our electrons in, we have single bonds here, as before, and of course a single bond here. However, the chlorine doesn't just have 1 electron, it has 7 in its outer shell, so we have 6 more. And now it's happy. Same as before, we've just switched out one of the hydrogens with a halogen, and we've had to add those extra electrons in. Now remember that Cl right there, that could be an F, it could be an I, it could be a Br. It could even be an AT, which is the bottom of the group 7, astatine, but is very, very rarely used in questions. Okay, so just one final example, just to make sure we got this. So we'll do chloroethane. So ethane was C2H6, but of course one of those has been replaced now with the chlorine. So again, we've got 2 carbons in the middle with single bonds of 3 hydrogens around one of them. And we'll have 2 hydrogens around the other with a chlorine atom. So let's just fill in our electrons. So 3 single bonds. So 1, 2, 3. Single bonds between the carbons. And then, of course, single bonds between the carbon and each of the atoms bonded to it. And the only thing to add, the only thing that makes this any different from ethane, is that we now have to add the electrons in to the chlorine so that it has 8, because it had 7 in the outer shell. So now when we count them up, we're obviously counting up 2 for each hydrogen, 8 for each carbon, and then of course 8 for the chlorine. And again, just like the last one, that chlorine right there, that could be a fluorine, a bromine, or an iodine, or perhaps, but like I said, very unlikely, an astatine. Okay, so there tends to be only 2 ways that this could be examined. You might be asked to describe the bonding in a covalently bonded substance for say 2 or 3 marks, whereby you would describe the electrostatic attraction between the positive nuclei and the negative shared pair of electrons. These would lead to strong attractions which require lots of energy to break. Now, for the dot and cross diagrams, for the second option, you could be given a variety of different options as we've seen, and I've gone through all of the potential molecules that it could ask you today. You just need to make sure that you have enough electrons in each atom and that your diagram is nice and clear. Okay, so that's the end of part 1. Stay tuned for part 2 coming soon. This has been Cardinal Science. I hope it's been useful for you. Please like and subscribe, or leave a comment below if you have any comments or questions. I'll be happy to help.